All right, so we were at definition of a monotonic sequence. Let me bring that up here. So it says if a sequence A sub n is monotonic, okay, so if a sequence is monotonic, then either A sub 1 is less than or equal to A sub 2 is less than or equal to A sub 3 less than or equal to ... less than or equal to A sub n less than or equal to etc. Okay, so this means that it's increasing or constant, okay, because you can see or equal to, right? But you'll notice every next term is bigger than or equal to the previous term, right? So if the next term is bigger than or equal to the previous term, then that means it's getting higher and higher and higher and higher. Okay, so it's increasing or constant. So if a sequence is monotonic, then either that is true, or you get A sub 1 greater than or equal to A sub 2 greater than or equal to A sub 3 greater than or equal to etc. greater than or equal to A sub n, which is greater than or equal to etc. Right? This would be a decreasing or constant function. Okay? So the reason why I write this out is sometimes when you have to prove that something is increasing or decreasing, you use this idea that all you have to do is show that the function itself is either smaller than or equal to itself on the next term, in other words, an n plus 1 term, or it's greater than or equal to itself on the next term. And I'll show you one of those examples right now. Okay? So we just have one example to do. Okay, and then that's it. So I forgot the number we were at. Which one were we at? I have 8 here, but I could be wrong. So we were on 6. So we're 5. Okay, so we're at 6. All right. Sometimes I like mix together some examples and I don't renumber them on my book that I write, but we did do them. So are these monotonic? Okay. So you're going to notice we're going to revisit stuff that we've done before, but we can still use it to apply to what we're doing right now. So the question for this one is this a monotonic sequence? Is it only increasing or only decreasing or staying constant, etc.? So we do A sub 1, right? We did this already. A sub 2, A sub 3, A sub 4. And we found it was 2, 4, 2, 4, right? So is this only increasing in constant or decreasing in constant? No, it's going up, down, up, down, up, down, right? So this is not monotonic. Now, this is one of the easiest ways to prove that something is monotonic or not, okay? Or actually, I'm sorry, let me rephrase that. It's one of the easiest ways to prove that something is not monotonic. So you disprove it by showing that some of the numbers are not working the way you want them to work. Well, let's look at B. So we'll try B sub n equal to n squared over 2 to the n minus 1. Okay, and I have some of these answers, so don't worry so much about calculating them. We're going to do B sub 1, so if we get 1 squared over 2 to the 1 minus 1, we get a 1. Okay, so fine. B sub 2, that's 2 squared over 2 squared minus 1. That's 4/3 or 1.3. Okay, that's 1.3 bar if I want to be exact, but 1.3. Okay, so far this function is increasing, right? B sub 3. That's 3 squared over 2 to the third minus 1. And that becomes 1.28. So what do you see? It's not monotonic. It increases and then it decreases, right? So it goes up a little and then it goes down a little, right? So not monotonic. So these are the best ones to get because there's no proof that you have to do. Okay, you just kind of say, look, the numbers don't do what they need to do. This is not monotonic. So obviously this last one has to be monotonic and we're going to have to prove it. Okay, so C sub n is equal to 2n over 1 plus n. So C sub 1, C sub 2, C sub 3. Let's do 3 of these things because you can't prove something is monotonic if it's just 2 points. Okay, you got to do a couple, more than a couple. So 3, 4, etc. So if we do C sub 1, we get 2 times 1 over 1 plus 1. So that's equal to 1. C sub 2 would be 2 times 2 over 1 plus 2. So that's 4 over 3 or 1.3 bar. Okay, so far it's increasing. C sub 3, that's 2 times 3 over 1 plus 3. So that's 3 over 2, which is 1.5. So what would you say is happening here? It's increasing, so this would be monotonic, right? But then someone would tell you, okay, but what happens like at C sub 4 and C sub 5 and C sub 6? And you'll say, oh, well, I'll show you. And then you calculate them and you're like, look, it's still going up. And I'm okay, well, what about at C7 through C50? Do you really want to do all of them? No, right? And then after you do those, if you were, I'd say, well, what about from 50 to 1,000,000? Does it ever not change direction? Right? So the only way you can do this, well, there's 2 ways. You could either do all of them and show me that it never changes, or prove it theoretically. Okay? So this is how you prove it theoretically. You're saying that this is increasing, right? So if it's increasing, I should be able to prove that C sub n is less than or equal to C sub n plus 1. If I can prove this, then I can prove to you that no matter what number I pick, it will always be bigger. Well, actually, sorry, let me rephrase that. No matter which nth term I pick, it'll always be less than or equal to the next one, right? Or you can say that the last term is always going to be bigger than or equal to the previous one, right? That's what I want to prove. Remember the definition I showed you guys, which is up here, that you can tell if something is increasing if the next term is always bigger or equal to the previous term, right? So I'm just going to do that, but theoretically. So C sub n is 2n over 1 plus n. C sub n plus 1 is 2 times n plus 1 over 1 plus n plus 1. Notice I'm just replacing the n value with an n plus 1. Now, by the way, if this comes out false, that means that at some point, I don't know when, this thing changes direction. Okay, so far, 1, 2, 3, they look good. But maybe at 25 to 26, they went back down, right? We don't know. If it comes out true, that means that this thing never changes direction. All right, so let's see. We got 2n over 1 plus n less than or equal to 2n plus 2 over n plus 2. Okay, I'm going to go ahead and cross multiply here. So I get 2n times n plus 2 is less than or equal to 2n plus 2 times n plus 1. Now I'm going to go ahead and kind of just distribute everything out. Okay, so 2n squared plus 4n is less than or equal to 2n squared plus 2n plus 2n plus 2. So that's 2n squared plus 4n less than or equal to 2n squared plus 4n plus 2. What can I do with the 2n squared and the 4n? I can combine them, but when I do, what happens to them? Yeah, they disappear. All this goes away. So I get 0 is less than or equal to 2. True statement? Yeah. So that means that my proof is correct. Why didn't I do anything with what? The bottom of the fraction? Oh, yeah, I cross multiplied. You're talking about from here to here, right? Yeah, I cross multiplied.
Oh. How did you get the initial statement that C sub n is less than or equal to C sub n?
Well, since I saw that this function was increasing, then the definition of increasing is that the previous term must be less than or equal to the next term, right? So I said, well, if C sub n is my previous function, then C sub n plus 1 would be my next function, right? But instead of talking numbers, I'm dealing with an equation. And if I can prove that the functions are true like that, then I've proven that it's always increasing. If somehow it said 0 is greater than or equal to 2, that's false. That means somewhere within all the numbers, it's going to change direction.
So should we do the C sub 1, 2, and 3 first, and then determine after we do that?
Yeah, you always want to do that because you don't want to start with the right side and the numbers were going down. If it started like 1.8.6, then you want to prove that C sub n is greater than or equal to C sub n plus 1. In other words, saying the previous terms were bigger than the next successive terms, right? So yeah, you always want to test a couple and not just one. Always do 3 or 4 because you might automatically find as you're doing those little number calculations that it's changing direction, so there's no need to do a proof, right? So and then once you know like, oh, this is going up or it's going down, then you'll know which function to use, either the greater than or equal to or the less than or equal to symbols.
If it didn't come out as true, would it be not monotonic?
Correct. Yeah, because we did see that it was increasing, and then if it comes out false, that means somewhere it decreased, right? So so yeah, this one would be monotonic. And if you want, you can just say that it's increasing. So what I just did right there, this portion over here, this is what math kind of looks like in college. It's not so, in college they say, I don't care if you can calculate stuff. That's great. Okay, you know how to add, you know how to subtract, good for you. Now, can you prove stuff for me? Can you show me you understand why when you add two numbers, it works? Right? Why does 1 plus 1 equal 2? And since that, and if you can prove to me that the addition idea is true, then we can now say that all addition must hold true. Right? So we start doing this weird stuff where we start calling, we lose all of our operations, addition, subtraction, multiplication,